How does a kinase differ from a phosphatase? Let me count the ways. It's easy to confuse kinases and phosphatases, especially if you consider the reversibility of reactions, but they're distinct types of enzymes. A kinase is going to transfer phosphoryl groups. Basically, we typically call these phosphate groups, but a phosphoryl group got this phosphorus and 3 oxygens instead of phosphorus and 4 oxygens. And one of the oxygens is coming from the attacking molecule. So from the substrate, the oxygen is going of the substrate is going to attack the phosphorus in your phosphate group, kicking this off. And so you're transferring this phosphoryl group rather than a phosphate group. But often we're just kind of lazy and we say phosphate group when we really mean a phosphoryl group. So apologies if I slip up. But what a kinase is going to be doing is it's going to be transferring that phosphoryl group between organic molecules. Often what it's doing is it's adding a phosphate group from an ATP, or remember it's a phosphoryl group, but typically we just say phosphate group. But it's going to be adding that from ATP or something similar to something to give you, leaving you with ADP. However, the reaction is also going to be reversible. And so remember that a enzyme catalyzes a reaction in both directions. So if there's similar energies and with taking into account the relative concentrations of the compounds, what we'll see is that this reaction can actually go in reverse. So we can use a kinase in order to make ATP from ADP by transferring a phosphate group from something else. In all those cases, however, we're doing it to and from organic molecules. So not free-floating phosphate groups, but instead phosphate groups that are present in some sort of quote-unquote high-energy bond. So this can be something like ATP, or it can be something with a higher free energy or a lower free energy. But basically, if we want to make ATP, we're going to want to have something with a higher free energy so that we can transfer a phosphate group from it onto ADP in order to make ATP. And so we'll look more into the details of this in a minute. But how does this differ from a phosphatase? A phosphatase removes phosphoryl groups through hydrolysis. So it's going to use water to break off that phosphate group. And so when you have something using water to break a bond, we call it a hydrolase. So phosphatases are hydrolases. They use water to break bonds. They catalyze hydrolysis. Kinases, on the other hand, are transferases. They're transferring functional groups. The functional group that they're transferring is going to be this phosphoryl group. Remember, we often just call it a phosphate group, but it is adding a phosphoryl group, not a phosphate group. So we don't have oxidation occurring when we have a phosphorylation reaction done by a kinase. Now, when we have a kinase catalyzing a reaction, well, just like any enzyme, a kinase is going to catalyze both the forward and the reverse directions. The directionality that is going to happen is going to depend on a couple things, just like the directionality of any sort of reaction. It's going to depend on the relative energies and concentrations of the molecules being transferred between. So ATP sits kind of like in the middle when it comes to the standard free energy of hydrolysis. What this is telling us is that the phosphate bonds in ATP, basically, they have an intermediate amount of energy that we would get if we were to break off that phosphate group. And so much more in the other videos about how basically by breaking off the phosphoryl group, we're freeing electric repulsion. Think of unclamping a spring. You also get the increased resonance, and you get hydration. You get all of that good stuff that's going to make this energetically favorable to hydrolyze it, which would make it energetically unfavorable to, well, add the phosphate group back onto ADP. But if you have a higher energy bond, well, then what you're going to be able to do is you're going to be able to use the energy from hydrolyzing that bond in order to put that phosphate group onto ADP. And so this is the standard free energy, but the actual free energy is also going to depend on our concentrations. So the delta G naught, or the delta G naught prime, which remember is just our biochemistry definition where we're taking the concentration of water to be 55 molar, we're taking the pH to be 7. And so in the standard conditions, basically what we can say is that if we have a really large negative delta G, it's going to be very favorable in the forward direction. And often when we have the hydrolysis of ATP, we're going to have a large negative delta G, because ATP, it's going to have this like quote unquote high energy bond. But because we have these higher energy bonds, we're then able to transfer the phosphate group onto the ADP. But the concentration of these things is also going to be taken into account, because this is the standard free energy, whereas the actual free energy is going to depend on our concentrations. If we have a fairly neutral delta G naught, and then what's going to happen is basically we can control the concentrations in order to control the directionality of the reaction. An example of this is what we see in our muscles with creatine and phosphocreatine, or creatine phosphate. Looking back at our standard free energies, we can see that phosphocreatine sits somewhat above adenosine, ATP, in terms of our delta G naught of hydrolysis. So it's a quote unquote higher energy bond. This means that we have energy in this bond that we can use to add a phosphate group onto ADP. But it's not like crazy amounts higher like we see with phosphoryl pyruvate. Instead, it's in the range where if we change the concentrations of ATP and of phosphocreatine, basically what we can do is we can skew the direction of the reaction. And this is what our muscles do. Creatine kinase, we'll see, is going to fit like any kinase. It is going to catalyze the reaction in the forward and reverse directions, and the actual directionality is going to depend in large part on the concentrations of ATP, phosphocreatine, creatine, and ADP. When ATP levels are high, the gamma phosphoryl group of ATP is going to get transferred onto creatine to give you phosphocreatine. So remember that this would be energetically unfavorable if we were just to consider the standard free energies, but we have to take into account the concentrations, and if we have a lot of ATP, this is going to drive things in the forward direction and give us phosphocreatine. When ATP levels are low, however, it's going to get transferred back to ADP to make more ATP. And all of that is going to be catalyzed by creatine kinase. So we can see that we're like quote unquote, removing a phosphate group. We're taking a phosphate group off of phosphocreatine and making ATP using a kinase, but we're also adding a phosphate group from ATP using a kinase. And the reason why we're able to go back and forth is because it has this delta G naught in which we can manipulate the concentrations in order to change the favorability of the reaction in one direction or another. Because remember that it's that concentration of products over reactants that's really going to influence which direction the reaction goes if you don't have a really large negative delta G. We see some examples of this in glycolysis. So if we have this step, where we go from 1,3-bisphosphoglycerate to 3-phosphoglycerate. So in the forward direction, we're basically removing a phosphate group from 1,3-bisphosphoglycerate, and we're transferring it onto ADP to give us ATP. And we can see by the two-sided arrows that this reaction is reversible, easily reversible. And in fact, if we go and we look at the free energy of this reaction, the actual free energy of this reaction in our cells, we see that it's about 0 to 2 kilojoules per mole. This is telling us that it's relatively neutral, and we can go, and it will go in either direction depending on the actual concentrations that are present within the cell. So we see that this phosphate group, this kinase, is catalyzing this reaction in both directions. In terms of its naming, when we name a kinase, it's in terms of what it's giving a phosphate group to. So we name it phosphoglycerate kinase because when it acts like in the forward direction, what it's doing is it's adding a phosphate group to 3-phosphoglycerate. So that's how we name kinases, is in terms of what they're actually going to be adding the phosphoryl group to. So we're adding the phosphoryl group to 3-phosphoglycerate to give us 1,3-bisphosphoglycerate. But we can also do the reverse direction and add the phosphate group to ADP, but we don't call it an ADP kinase. That wouldn't be very helpful of a name. We call it phosphoglycerate kinase. This one was easily reversible, but not all of them are. So one that's not very easily reversible is going to be this step in which we dephosphorylate PEP, so phosphoenolpyruvate, when we basically take the phosphate group or the phosphoryl group, remember, from phosphoenolpyruvate, transfer it to ADP to give us ATP. If we look at the free energy of this in erythrocytes, so in red blood cells, we see that it's about negative 16.7. This is going to be very hard to reverse. We can see that the negative, that it has a very large G naught, delta G naught, which corresponds to up here, we see how high energy this phosphoenolpyruvate is. So we have lots of energy here, plenty of energy in order to transfer that phosphate group onto the ADP. Why is this? It's actually pretty cool. Basically what happens is that there's this thing called tautomerization, where we can go between an enol and a keto. So in enols, when you have alkene, so two carbons double bonded, and one of them is attached to an alcohol group, so enol. Now this can tautomerize to the keto form. So basically, if you imagine that the electrons from here get pushed over to here, you can form a double bond to this oxygen. You just need a proton transfer, and then what you're going to get is this keto form. Now, what do you think would rather have those electrons, the oxygen or the carbon? It's going to be the oxygen. So this keto form is going to be highly favored. But when you have phosphoenolpyruvate, basically what you have here is the phosphor group is going to be trapping this in the enol form. If you remove that phosphate group, what's going to happen is it can now tautomerize to the keto form, which is highly favored. And so that's going to give you this big boost of energy that you can use to catalyze the addition of that phosphoryl group onto ADP in order to give you ATP. This is also a great example of the kinase naming, because we call this pyruvate kinase, the enzyme that does this, because it would be phosphorylating pyruvate to give us phosphoenolpyruvate. But instead, it's kind of like dephosphorylating it. And instead, it's phosphorylating ADP. But remember that we don't call something an ADP kinase, really. Instead, we think about what it would be, the more exciting thing it would be phosphorylating. So that would be pyruvate. And in fact, it would be really exciting if pyruvate was phosphorylated, because that would be so hard to reverse this reaction because of that really large negative delta G. So don't get confused by the naming. Pyruvate kinase, it would phosphorylate pyruvate. It could phosphorylate pyruvate, but that's not going to happen in vivo. And so instead, what you see is more of this like dephosphorylation reaction, but this is not happening by a phosphatase. This is happening by a kinase. We're not using water to break this off. Instead, we're transferring it from this phosphoenolpyruvate onto ADP, and that's going to generate ATP and leave us with pyruvate. So you get some of these kinase reactions are going to be very, very hard to reverse. So often instead of just simply using a kinase to go in the reverse direction and try to take that phosphate group back off of ATP and stick it onto the pyruvate, what you instead do is basically you would just hydrolyze it. In this case, it's not a very good example because we would just be hydrolyzing ATP. But you can imagine, what about that first step in glycolysis, where you actually want to remove the phosphate group. You would actually want to remove the phosphate group from glucose-6-phosphate in order to give you glucose in gluconeogenesis. Well, when we have steps like these are actually going to be reversed, not just by changing the concentrations, but by changing the enzymes that we use in the different directions. And so this is when we'd want to use a phosphatase. So a phosphatase, remember, is going to use water to break things off. It's a hydrolase. So instead of going and trying to take that phosphate group from glucose-6-phosphate and stick it onto ADP to give us ATP, what we're instead going to do is we're just going to use water to cut off that phosphate group. You can see that we're not going to generate ATP in this case. Instead, we're just going to get a free-floating phosphate group, this inorganic phosphate, this like orthophosphate, where it's just like a single phosphate group freely floating around. Now, this, like all reactions, everything is theoretically reversible. However, if we imagine how we could reverse this reaction, knowing that it has a really large negative delta G, and that's the concentration of water is 55 molar. If we wanted to manipulate the concentrations in order to kind of drive this reaction in the other direction, to take that phosphate group, that inorganic phosphate group, and just add it back to our substrate, well, we would need to have our substrate at such high concentrations. It wouldn't really be actually like, I don't even know if you could have that high of concentrations of something in even, not even in your cells, just in vitro. That would be ridiculous. Like, I don't know the solubility of these things. Water is basically so crazy high in molarity that you're not going to be able to outdo it in that sense. So these phosphatases, the reactions that they catalyze, are typically going to be pretty much irreversible. We're not going to have a phosphatase go in the other direction. We have kinases and phosphatases often acting in pairs, where we have a kinase phosphorylate something such as a protein, and then we have a phosphatase remove it. And this is going to be really, really important for things like signaling pathways. We wouldn't want the kinase to just be adding and taking off phosphate groups willy-nilly, depending on relative concentrations. That wouldn't make for a very good signal system. Instead, we want the signal to be able to be removed on demand and by regulation, which we can do by regulating the phosphatase. So if a kinase adds a phosphate group, it can change the activity of a protein, it can activate a pathway, it can do all sorts of stuff. And we can regulate the kinase in order to regulate when that gets added. Then if we want to turn off that signal, if we want to deactivate the protein, if we want to do this sort of thing, we want to be able to do so quickly. And the way we can do so quickly is by basically regulating the phosphatase. So having the phosphatase then remove the phosphate group on demand in order to stop the signal or in order to change the activity of the protein. By having these kinases and the phosphatase work in pairs, we're able to do this. There's a step in glycolysis in which we actually use an inorganic phosphate group in order to add it on. In this glyceraldehyde 3-phosphate dehydrogenase step, we're taking an inorganic phosphate and we're adding it to glyceraldehyde 3-phosphate to give us 1,3-bisphosphoglycerate. In the case of this hexokinase step or this phosphofructose kinase step, we didn't have the energy that we would need in order to go backwards. We couldn't just have enough energy in this inorganic phosphate to directly add it back on. Here, we're getting energy from this oxidation reaction through this coupling. The oxidation of glyceraldehyde 3-phosphate to give us 1,3-bisphosphoglycerate. Basically, you can see it's oxidation because we're actually adding this whole phosphate group rather than a phosphoryl group. So we're adding enough extra oxygen. The oxygen isn't coming directly from the molecule. When you have a kinase, remember that one of the oxygens is going to be coming from the substrate. So you could have, say, a serine in the protein, which is going to be deprotonated to give us the strong nucleophile that's going to then attack this phosphate group. It's going to attack the phosphorus, which is going to be our electrophile because the oxygens are pulling away electron density. This is going to push off the ADP and leave us with the transfer of this phosphoryl group. Because you have this one oxygen coming from the substrate itself, this is not going to be an oxidation reaction. Instead, because we're transferring that phosphoryl group, it's not an oxidation. So remember, we often say it transfers a phosphate group, but a kinase is transferring a phosphoryl group. In the case of this reaction, what we have is we actually have a whole phosphate group being transferred. We see that an oxidation is occurring. This carbon is forming more bonds to oxygen, fewer bonds to hydrogen. This means it's going to be losing electrons or electron density and giving it to NAD+. That's going to be energetically favorable, and it's going to have enough energy in order to power the addition of this inorganic phosphate onto glyceraldehyde 3-phosphate. So in this case, we're able to add from an inorganic phosphate, but we wouldn't have enough energy to add it if we didn't do it that way. Now, one last note before we go. Don't confuse a phosphatase with a phosphorylase. A phosphorylase is going to break bonds with inorganic phosphate groups. So remember, we talk about inorganic phosphate, that's distinguishing it from something like ATP, something with carbons, one of those quote unquote high energy phosphate bonds. Instead, we just have something like a free floating phosphate group. What this is able to do is, with the help of an enzyme, it can go and it can actually break bonds. So it can break these glycosidic bonds. And this is going to allow you to break down molecules like glycogen, breaking a bond and transferring that to inorganic phosphate. So it's still a transferase, but it's not transferring it from an organic molecule, it's transferring it from an inorganic molecule. So glycogen phosphorylase is our classic phosphorylase. Often it's just referred to as phosphorylase, but there are other phosphorylases as well. This one is going to break down our glycogen, so our storage glucose, in order to give us a shorter glycogen as well as glucose 1-phosphate. So by doing this breaking with actually adding the phosphate group in the process, well, now this glucose 1-phosphate has energy to go and be used in various processes. You just have to basically do an isomerization, and you quickly get to glucose 6-phosphate, which can do things like interglycolysis. Remember, there was that step when we're adding a phosphate group, an inorganic phosphate group, onto a molecule in glycolysis. That was our glyceraldehyde 3-phosphate dehydrogenase, but that was not a phosphorylase, because what's going to be happening there is we're not breaking anything. We're just adding this phosphate group on. We're not breaking a bond in the process. When we have a phosphorylase, basically what it's going to be doing is it's going to be getting its energy from the bond. That's going to have the energy in order to power this addition. So this glycosidic bond is going to be basically storing energy. You are going to then use the energy stored in that bond in order to power the addition of the phosphate group. In the case of our glyceraldehyde 3-phosphate, the addition of the phosphate group there, that's going to be the energy for that is going to be powered by the oxidation. To review, a kinase is going to transfer phosphoryl groups between organic molecules. So this is often going to be from, say, ATP onto a protein or onto a small molecule. The key is that you're transferring these groups to and from organic molecules. With the phosphatase, you're going to be removing phosphoryl groups through hydrolysis. So here you're using water to break the bond. And you're typically going to just be breaking the phosphate group off because it would be practically irreversible to add it back on. However, with a kinase, the reactions are often reversible, and this reversibility was going to depend on the relative concentrations of these things, as well as the differences in free energy between them. So some of these bonds, if they have a similar free energy, you're going to be able to reverse them based on concentrations, such as this step of 1,3-bisphosphoglycerate to 3-phosphoglycerate in glycolysis. However, other steps are going to have such a large negative delta G that it's going to be practically irreversible. In this case, an example of this would be our hexokinase steps and our phosphofructokinase steps. In these cases, instead of trying to transfer the phosphate group back off of these molecules and onto ADP in order to reverse this, we would want a phosphatase, which would basically just use water to cleave this off. And in fact, this is what we see in gluconeogenesis. We bypass these steps that were taken in glycolysis using these phosphatases, fructose 1,6-bisphosphatase and glucose 6-phosphatase. It's helpful to be able to therefore regulate the kinase and regulate the phosphatase individually in order to quickly influence the activity, the directionality of a pathway. Especially you can do things like a whole pathway, because often those ATP, the addition of a phosphate group is going to have a very large negative delta G. Not always, because remember, some of these are going to be easily reversible, but a lot of our phosphorylation steps are going to be hard to reverse, and this is going to make them good points for regulation and for driving pathways, as well as for coupling unfavorable reactions to this favorable reaction. So that is your basics of kinases and phosphatases, and hope that helped.